Okay. Assalamu alaikum and good morning, everyone. So today the format of class will be a bit different as Professor Iqbal is traveling currently. So we will start with playing two videos that will cover the aspects that Sir has already taught you, and that will be followed by a short NMR quiz, and then Dr. Atya will take the rest of the class. So I'm going to start the video.
Works,
You can ask question in between if you want.
its principles, and how to read the data. And here are our key points here. Number one, we're going to see, because of its charge and spin, a nucleus can behave like a... This online lecture is an introduction to how the NMR machine works, its principles, and how to read the data. And here are our key points here. Number one, we're going to see, because of its charge and spin, a nucleus can behave like a magnet. We're also going to see, number two, that NMR spectroscopy operates by applying a magnetic field to nuclei and then measuring the amount of energy necessary to put various nuclei in what's called resonance. And number three, we're also going to see here that nuclei in different electronic environments, that is either being shielded or de-shielded, require different amounts of energy to bring them into resonance. And we're also going to see, number four, an NMR spectrum provides a signal or peak representing the energy necessary to bring each nuclei into resonance. All of these are very profound, so let's make sure we walk through this and get all of them here. And we'll start with our first key point. Consider the hydrogen atom. Remember, what he simply is a proton with one electron circulating around him. What's very key here, though, is that this proton right here has a certain spin, let's say. And because of its spin, it just so happens to give hydrogen atoms a property that makes them behave like magnets. So you could almost think of a hydrogen atom acting as a magnet. Why is this so? This is way beyond organic chemistry. That's a job for physics. We just have to know that hydrogens can behave like magnets. But they're not the only atoms that can behave like magnets. Technically, any one of these atoms right here can behave as magnets. The key features are, one, having an odd number of protons, or you have an odd number of neutrons, or simply you have both. Any atoms with these characteristics will behave like a magnet. Now, let me show you an alternative way to represent a magnet. Instead of drawing pictures like this, you can actually represent a magnet almost like a vector, with the arrow pointing towards the north end of the magnet and the other side on the south end of the magnet. What this simply does is enable us to represent our magnet in different orientations, such as pointing to the upper right-hand corner like you see here, or pointing down like this, or like this, any way we want. In this section, this is how we're going to be representing our magnets. Let's also remind ourselves of how magnets behave. Maybe you've had them or played with them when you were a little kid, and you might remember that when you take one magnet, let's say this blue one, and stick it close to another magnet, it has an effect on that magnet. What would happen is the north ends of these magnets would repel each other, and the north would be attracted to the south end of the magnet. So in response here, the pink magnet would move this way, like this. So what we're seeing here is that magnets can affect the orientation of other magnets. But let's look at this through the eyes of physics here. One way to conceptualize magnets is to think of them as being surrounded by magnetic fields. and these magnetic fields have directions and magnitudes. So for instance, for our blue magnet here, we can say that he's generating a magnetic field this way. And typically, magnetic fields are given the symbol B. So another way to understand the influence of magnetic fields is that if we again move this magnet close to the other pink magnet here, then the result is that this pink magnet orients itself with the magnetic field in this direction. In this section, we're going to be representing magnetic fields as these blue arrows, which from now on, as you can see here, are going to influence the orientation of other magnets. So now let's talk about what happens when we stick these magnets in a machine such as the NMR. Let's say we're putting this in our NMR like this right here. And just think of the NMR as simply containing a chamber where a magnet or a sample could be inserted, and that chamber is being influenced by a big magnet here in red. And let's even do this. Let's represent our magnet as our vector here like this. This is expressing his orientation. And let's say, for instance, we turn on the magnet of the NMR, and when that magnet gets turned on, this is the direction of the magnetic field that he creates. And we're going to call that the applied magnetic field. It's simply the magnetic field applied by the magnet in the NMR. Now remember, what effect would that have on our magnetic here? Well, remember, he will orient himself with the magnetic field like this. And let's pause for some vocab here. If this happens, we are saying that this magnet is in what's called the alpha spin state. And we need to know that this particular state is considered the lower energy state, or more stable state. However, this is not the only possible outcome here. Let's go back to the beginning here. Again, if we turn on our NMR machine and the applied magnetic field runs in this direction, then it's also possible that your magnet could get stuck in this orientation. Notice it's parallel to the magnetic field but pointing in the exact opposite direction. In this section, we're going to call this the beta spin state. And we need to know that this would be the higher energy state. We should also understand that very few magnets would actually do something like this. Most magnets would orient themselves with the magnetic field in the alpha spin state. So now let's apply what we just learned here to an actual H atom. And again, let's represent our H atom as some kind of magnet with this orientation. And let's pretend he's in some particular environment. And let's pretend on the right side of our screen we have another H atom, and this happens to be his magnetic orientation. But let's say his environment is different from the one on the left. For instance, let's say he just so happens to be surrounded by many electrons. Now, if this is the case, let's pretend we stick both of these separately in the NMR machine. And let's focus on the left side first. Again, if we turn on the NMR and the magnetic field runs this way, then we can expect the H atom to orient himself with the magnetic field like this. However, what happens to the nuclei on the right? How does the electrons change things here? Well, first of all, we should know that what's happening is this H atom on the right would have something called diamagnetic shielding, which simply means he's being shielded by these electrons. And shielded from what? Well, in this case, shielded from the effect of the magnetic field applied by the NMR machine. So look at this diagram here. It's almost as if these electrons are shielding it or protecting it from the applied magnetic field. Which means this hydrogen atom on the right here is most likely not going to change his orientation. He'll stay exactly how he is. However, what if we do something like this? Let's say we hook up some kind of light source. And this light source has the ability to produce RF radiation, or radio frequency radiation. Remember, this is a form of electromagnetic radiation, which means this light is carrying energy and delivering its energy to the H atom. What can possibly happen here is that the light energy could give this H atom enough energy to move into the beta spin state like this, which remember is the higher energy position. Let's call this energy E1. So E1 is the amount of energy necessary to bring the left H atom into the beta spin state. Now let's do the same thing to the H atom on the right here. Again, we set up our light source here, we shine radiation at him, and the radiation is going to deliver energy to him. And let's say we give enough radiation energy here to knock him into the beta spin state. Let's call that E2. So E2 is the energy necessary to bring the right-hand H atom into the beta spin state. Now, let's pause for a second here for vocab. What we would say here is that both of these H atoms, now both oriented in the same direction, that is up, we would say that these H atoms or nuclei are in what's called resonance. Resonance meaning same. And think about E1 here, this energy, compared to E2 energy. What would be their relative amounts? Meaning which H atom would require more energy to bring it into resonance? Well, think about it. The H atom on the left has to turn one full 180-degree turn. If you notice, that's a much greater distance of travel than the H atom on the right. He only has to just turn just a little bit to go to the beta state. So that means energy 1 must be a higher value or more than energy 2. Now, what does this all mean? Well, let's see what the NMR would deliver as its data for what we have in front of us here. What it would do is spit out this chart that looks like this, and let's pretend on the x-axis is energy. And if we put each one of these H atoms in the NMR, this is the data that it would report. We would simply see two signals, or sometimes called peaks. Each one of these signals would correspond to the amount of energy necessary to bring a particular H atom or nuclei into resonance. For instance, this one right here would be E1 on the left, and the signal on the right would be E2. So for instance, going back to our diagram, let's say we're representing the left hydrogen as A, then this signal right here is due to that A hydrogen. And if we represent the other H atom as B, this would be the signal right here for him. So think about what we're seeing here. Seeing two peaks in the HNMR data technically means that you have two hydrogen atoms in different electronic environments. And let's pause for some vocab here to describe those environments. If you are an H atom surrounded by a bunch of electrons, you're considered to be in a shielded environment. And that would be hydrogen B here. If you don't have a lot of electrons surrounding you, you're considered to be in a de-shielded environment, like hydrogen A. What we proved before was that if you are in a shielded environment, it takes a lower amount of energy to bring you into resonance, and it takes a higher amount of energy to bring a de-shielded hydrogen into resonance. Now, you might be wondering at this point, hey, this is great, but what does this have to do with organic chemistry? And what is the NR machine actually doing for me here? Well, let's look at an actual organic molecule here. Here we have chloroethane. Let's take a look at the type of environment each of the hydrogens here in chloroethane would be in. For instance, let's focus on these hydrogens right here first. Let's represent them as a magnet with this particular orientation. Remember, this magnet represents the nuclei of the H atom, and that nuclei happens to be surrounded by electrons. Where did these electrons come from? Remember, these are atoms. We got carbon, Cl, we got hydrogen. Each atom has protons and electrons. However, remember the principle here. This chlorine is very electronegative. And remember, that means that he attracts electrons. So he in turn would have an influence on the electrons surrounding that H atom. He would pull the electrons this way. What that would effectively do here is make this hydrogen very de-shielded. He simply has no electrons around him, or very few. Compare this electronic environment to these hydrogens right here on the end methyl. Again, let's say this happens to be their magnetic orientation, and let's say these happen to be the electrons that surround them. If you remember correctly here, Electronegativity is a local effect. For instance, as you see in this diagram, the electronegativity would only extend to this green bubble here. So any electrons in that vicinity will be sharply moved to the Cl. But the ones not in that bubble will not have as much of a pulling effect. So in other words, the further you are from an electronegative atom, the less the effect of electronegativity. So going back to our example here, since the 3 methyl hydrogens are further away from the Cl, we expect less of an electronegative pull on them, which means they will remain around those H atoms, and therefore make them more shielded. So let's do this. Let's pretend we take our molecule and stick him in the NMR machine. What we saw, remember, is that if you are a hydrogen that is more shielded, it takes lower energy to bring you into resonance. And again, if you're a more de-shielded H atom, then it takes a higher amount of energy to bring you into resonance. So, what would the NMR spit out as its data for this sample molecule? Well, let's see here. Let's label our hydrogens first. Remember, let's call this guy the A hydrogen, and we'll call these 3 hydrogens the B-type hydrogens. Putting this sample molecule in the NMR would give us a spectrum that looks like this. We can expect to see 2 signals in it. Remember, one for the A-type hydrogens and 1 signal for the B-type hydrogens. And those 2 signals again will correspond to the amount of energy necessary to bring these hydrogens into resonance. Now at this point you might be thinking, okay, that's great, that's the connection of this to organic chemistry, but still, what does this do for me? Well, I'll get to that in a second, but let's pause for some vocab here. If you get a good look at this spectrum right here, here's what I want you to know. If you're more de-shielded, and again, which means it takes a higher energy to bring you into resonance, and if you're more shielded, let's say, which requires a lower energy to bring you into resonance, the de-shielded peak, what we want to know, would be more downfield. Notice here in your chart, your 0 is on the right-hand side. So a downfield peak is more away from the 0 mark, whereas any peaks that are closer to 0 would be considered upfield peaks. I'm going to be using these terms a lot when we're interpreting NMR spectra. So now, finally here, what does this NMR machine do for us? Well, let's just say you happen to have a sample. In this beaker is some organic substance. And let's say we take this substance right here and we run it through the mass spec. We learned how this machine worked in a previous online lecture, and remember, he had the ability to deliver not only the molecular weight of a compound, but also the possible molecular formula. And let's just say the mass spec happens to say that our sample is C3H7Cl. Let's say we also run it in the IR spec machine, and the IR spec tells us that we see a lot of CH vibrations. Of course, because there's a lot of CH bonds in our molecule. Remember, we also learned how this machine works in a previous online lecture. And notice, if we did a calculation on the degree of unsaturation of our sample, the degree of unsaturation is 0. We talked about how to do this also in another online lecture. And remember, what this 0 means is that our molecule has no double bonds, no triple bonds, or no rings. Now, think about what structures might fit the data at this point. Your molecule could possibly be 1-chloropropane. Notice this molecule does have 3 carbons, 7 hydrogens, and 1 Cl. However, your molecule can also possibly be 2-chloropropane. And if you thought a little bit more about this, you'd realize there's no other possibility. There's no other organic molecule that would have this molecular formula and not be either 1-chloropropane or 2-chloropropane. So at this point, we don't know if it's one or the other. Here's where the NMR is going to help us. Notice, let's place our molecules side by side here. And let's think about the electronic environments of each of the hydrogens in each molecule. So let's start with 1-chloropropane first. Remember, he has this Cl right here, which means these hydrogens right here, let's call them the A hydrogens. Since they're the closest to the electronegative Cl, they would be the most de-shielded. Whereas the hydrogens way on the other end over here, these guys, let's call them B, these would be the most shielded because they're the furthest away from Cl. And these hydrogens right here in the middle, we'll call them the C hydrogens. They'd be, let's say, middle of the road, not as de-shielded as A, and not as shielded as B, somewhere in the middle. Which means technically, for this molecule, you have 3 hydrogens and 3 different electronic environments. Which again means if we run this through the NMR and look at the data, we should expect to see 3 signals in the HNMR. Again, 1 signal each for bringing each one of these hydrogens, A, B, and C, into resonance. And why not? Let's label him. Remember, this guy would be our A hydrogen peak, the most de-shielded. This right here would be the B peak, the most shielded. And then remember, C right here would be in the middle of them. So that's what we would get out of the HNMR for that molecule. Now let's do the same type of analysis on 2-chloropropane. Again, we focus on his Cl right here being very electronegative. And let's call this hydrogen right here the A-type hydrogen. Notice out of all the hydrogens in this molecule, he's the closest to Cl. So he should be the most de-shielded hydrogen. Now, what about the hydrogens on the left here? Let's call them the B-type hydrogens. Notice, whatever they are, they're definitely going to be less de-shielded, simply because they're further away from the Cl than the A hydrogen is. But what about these hydrogens over here? Notice they are an equal distance to the Cl as the B-type hydrogens. So that means these hydrogens are roughly in the same electronic environment. The amount of energy to bring them into resonance would be the same, which means we can also call them therefore B-type hydrogens.
Okay, so what kind of spectra are you expecting for this molecule? 2 signals.
One small one.
Good. Because of the same chemical environment of those H3.
They are literally equivalent. So what does that mean here? Again, what would the NMR spit out as its data? Since there are technically 2 types of hydrogens in this molecule, A and B, we should expect to only see 2 signals in his HNMR spectra. This would be the signal for the A-type hydrogen, and this would be the signal for the B-type hydrogens. Again, the reason why we're only seeing 2 signals here is that all the B hydrogens, since they have the same amount of energy to bring them into resonance, all of them would peak on top of each other. They would simply overlap in the data. So that's why we would only see 2 peaks in his spectrum. So notice it's the HNMR that helps us distinguish these 2 structures, which means if we throw our unknown sample into the HNMR and we see 3 signals, we know the molecule has to be 1-chloropropane. If we happen to see 2 signals, we know the molecule therefore must be 2-chloropropane. So notice, in summary here, by using all of our available machines here, and that is the mass spec, the IR, and the NMR, we can unequivocally determine what our sample molecule is. And take note here, notice it's the combination of more than one machine that's helping us determine the identity of an unknown sample. Each machine plays a very important role. So let's pull it all together here. What have we learned? All right, here's our key points, right? Remember, 1, because of its charge and spin, a nucleus can behave like a magnet. That's very central. We saw that. Number 2, NMR spectroscopy operates by applying a magnetic field to a nuclei and then measuring the amount of energy necessary to put various nuclei in resonance, right? That's key. That's the whole chapter right there, the essence of it. That's what we're leaning on. This is the science behind the concept of how this machine works. Let's look at number 3 here. 3 says nuclei in different electronic environments, in that case shielded or de-shielded, require different amounts of energy to bring them into resonance. Another very important key point. And 4 here, an NMR spectrum provides a signal or peak representing the energy necessary to bring each nuclei into resonance. And this, we're going to see, helps us determine structure.
Okay, so this was the video, and I would like you guys to watch this video again, and so you can have a revision. And now we will start with a short NMR quiz. I'm going to distribute for these physical participants And for the online participants, can we
You have
share it in the chat box?
I think Dr. Hina has shared that 90% of this there. आगे नीचे आगे
Okay, so for online participants, kindly respond if you have received the short quiz of NMR. No discussions, please. Quiz है. Okay, in question number 7, and kindly look at question number 7. I think it's written N15. It's a typographical error. It's N14. Online participants, please listen that in question number 7, it's not N15, it's N14. Correct it and then answer your question. Who done?
हमारा कितना नहीं लो they will mark that. पेपर नहीं अरे Okay, students, let me know when you finish your test. So we are giving you 5 more minutes to complete the quiz. Then we will discuss the answer of this question.
Okay, so for the online participants, you don't need to submit it anywhere. Just wait for 5 more minutes, then we will discuss the questions and you can mark yourself. Okay, so keep your test with you.
Okay, students, now we are going to discuss the questions. So, how many of you think that the uh, which which of the following could be considered as the lowest energy form of the electromagnetic radiation? The correct answer is D. So, please mark yourself. And then for yes, for the second question, the correct answer is D. And if you want to discuss any question, we can discuss that after I will give you the answer of all these questions. Uh, D for delta, and then for the question number 3, the answer is D. 3, question number 3. For question number 1, the correct answer is D. For question number 2, the correct answer is D, D for delta. And for question number 3, the correct answer is D. For question number 4, the correct answer is D. Yes. Again, for question number 5, the correct answer is D. For question number 6, the correct answer is B, not D. Okay. For question number 7, the correct answer is C, right. And for question number 8, the correct answer is again D. And for question number 9, it's B. Okay. And for question number 10, the correct answer is yes, the correct answer is C. So, how many of you got 10 marks? Good. Collect clap for yourself. Okay, so now Dr. Atya is going to take the class. Over to you, ma'am.
Assalamu alaikum, everyone. I would like to ask from online participants if you can hear my voice clearly. In case if voice is not clear, please send a message in the chat box. And I request Dr. Sumaira and Mara to kindly look at the chat box. Okay, so today we'll be discussing about the practical aspects of NMR analysis. As a matter of fact, this is not the, we will be discussing about a small molecule, and then we will be discussing about the practical aspects of uh, small molecule and the large molecule mixture of it, using different interaction studies, for example, STD NMR, and then we will be also discussing a very few aspects of large molecular NMR spectroscopy. So that is the same. The theory that you guys has been studying so far in last two classes is the same. But for large molecule and the small molecule, there are some difference in NMR spectroscopy, but not in terms of analysis, because in large molecule, we usually have to have 3D NMR or 4D or 5D NMR. And then, and most of the analysis need to be done on computer. On 3D, you cannot plot and on the spectrum one page, which is the page that you have is a two-dimensional page. So we cannot have the 3D spectrum on this. So that is why there are some difference, but we will be discussing this later on, not now. So so today we'll be discussing about how to prepare the sample for the spectroscopic analysis and logical approaches that we need to follow for this structural elucidation, and various NMR spectroscopic techniques and their systematic use. Structural elucidation of organic compound will start structural elucidation practicing together from a small molecule, and then we will go to the large molecule. And NMR spectral analysis exercise is a part of the structural elucidation. Other applications of NMR uses biochemical structure elucidation. This is the toughest part, I think, and the drug discovery by using NMR spectroscopy. So this is the content that we will be discussing, not all in today's class. So we will be discussing, Dr. Iqbal will be discussing the theory of NMR spectroscopy, and me, Dr. Sumaira, and Dr. Humaira will be discussing with you practical aspects of NMR spectroscopy. Okay, so let's talk about small molecular NMR. And if you have a sample with you, which is a small molecule means usually organic molecules. And these molecules are very small, is usually few hundred daltons, not more than that, as 300 daltons or maybe 600, or maximum if you go, maybe it's a big structure, dimer or trimer, some kind of structure like this, then maybe 800 or 900 daltons. But if you talk about the large molecule, it start from 400 or start from, I would say, like 900 daltons as a small, medium size, very smaller size of the peptide. And that is 900 dalton means 900 kilodaltons. So that is 9 kDa. And and that requires, that's a smaller size of the peptide. And if we can go further, the spectral analysis get more and more complex. And we have a limitation in NMR spectroscopy than so far with the available magnet, which is 1.2 gigahertz. We can go up to 35 kilodalton protein, not more than that. For more than that, we still need to rely on X-ray. And now we have cryo-electron microscopy as well, but cryo-electron is just give the bigger structure, bigger molecular structure overall. but not at the atomic level. Okay, so let's come back to the small molecules. Okay, so when you have the molecule, when you obtain the molecule, and that could be from natural sources, or you may have synthesized this molecule, but it's a small molecule, few hundred daltons, a very small molecule. So you purify using different techniques, using HPLC, using TLC, using column chromatography, various techniques you have to follow. That is chromatographic techniques, various chromatographic techniques based on the nature of the compound you need to obtain to purify your compound. Either you synthesize it or you isolate it from any natural sources. So once you have any compound and you purify, so you would like to see if it is pure or not pure. So if it is pure on TLC, this is the first thing. All right, and if you want to check the more purity and very much in that, you have to use UPLC, and that is ultra high performance liquid chromatography, and you can easily that's a very small quantity that you need to inject, and you can find if your compound is very pure or not. But TLC is very handy and very easily every lab can do it. So if you have a pure compound, if you do not have the pure compound, you cannot proceed for it. And if you have the pure compound, you need to weigh the sample. And if you have more than 2 millimolar sample, then you can proceed. And if you do not have that much quantity of the sample, then you cannot proceed further. There is no use of it because you cannot done all the spectroscopic analysis. And because you have to use IR, UV, mass, different type of mass spectroscopic technique, and mass is destructive technique, and then NMR. And then NMR is, as so far you have been discussed, that it's the most insensitive technique. So that is why, though we have the highest the most advanced electronics with us, even then you need some few milligrams of the compound to proceed further. While in case of UV, for example, in IR, if you have 0.1 or mass, even if you have 0.1 milligram, 0.1 milligram, I'm not talking about 1 milligram, 0.1 milligram, even then you can proceed. But definitely, you will be consuming your compounds using mass spectroscopy analysis. So you need to have few milligram of the compounds if you would like to proceed further. Okay, so if you have more than 2 milligram of the compound, you would like to check the solubility. You already have some idea in which, because of the chromatography you already done, but you still need, because maybe you are using some kind of techniques, some kind of solvent that we do not have as a deuterated solvent. So here is a limitation. So we need to check if this compound would be soluble in the available deuterated solvent, but it doesn't mean that you will use deuterated solvent to check the solubility. You need to check the solubility in non-deuterated solvent, okay? Because if your compound it's not soluble in the solvent, here in our and that's so far that we are studying is solution NMR spectroscopy, and we have all the 13 NMR equipment that are solution phase NMR. We cannot study in our institute, and I think in Pakistan we do not have any solid state NMR yet. Okay, and so if that's why solubility is extremely important. If you have a compound, a pure compound, so you need to check if your compound is soluble in the commonly used deuterated solvent. right? And there are many other uncommon deuterated solvents are also available, but that's are not available in the facility. So maybe if you want to use, you may ask your supervisor to purchase the deuterated solvent for you. There are many type of deuterated solvents available, but we have usually the one which are common one in which most of the organic compounds are easily soluble. For example, chloroform, deuterated chloroform, and then deuterated water, D2O. And we have methanol, deuterated methanol, very commonly used. And we also have deuterated pyridine and DMSO. These are all deuterated one. Yeah, but we do not have ethyl acetate. Like, for example, it's common solvent, but we do not have it. Yeah.
As you said, it's not soluble. How many isolated techniques?
No, I'm not saying this is not soluble. I said you need to check the solubility in the maybe, for example, if you have used ethyl acetate, for example, to isolate or purify your compounds, and now in our facility we do not have ethyl acetate deuterated. So then you need to check the solubility of your compound if it is soluble in chloroform, in methanol, or in the mixture of chloroform or methanol, or in DMSO, or in pyridine. You know, these are the solvents that are available. But definitely, as I said, there are many solvents, deuterated solvents, which are available commercially. But we have the most common one in the facility for students. But if you like to have any specific one, then you can request your supervisor to purchase it. Then you can use that particular solvent in NMR lab. And deuterated solvents are extremely expensive and they are getting more and more expensive. Okay, so if, for example, if, or hexane, we do not have hexane, deuterated hexane with us, right? So if you would like to solubilize your compound in hexane, we can say, okay, you can bring your deuterated solvent. So we do not have deuterated hexane with us, right? So that's mean the solubility. And based on the solubility, you can, yes.
Why we rated solvent?
Okay, so we need to, there are, so far, you have studied that there is a big magnet, right? But there are, and you are giving the radio frequency because with the passage of time, and if you want to keep the stability, the homogeneity constant, you do not want there is some kind of deviation because of the constant pulse that your sample is being receiving. So there is a change in temperature. You know, change in temperature means your chemical shift will change. You know, it's very, very sensitive technique. It's sensitive in a sense that every change has an effect. So, and since you are giving the radio frequency, and you may notice that whenever you go to the NMR lab, or if you have seen in your spectra, there are dummy scans, right? In dummy scans, we do because we want to stabilize our sample, and there during these dummy scans, the sample is receiving the radio frequency, but nothing is recording because we would like to stabilize the frequency. And if we are, and it's not necessary, of course, to use the deuterated solvent. We can use non-deuterated solvent which doesn't have the hydrogen. Or, you know, for example, carbon tetrachloride, CCl4, you can definitely use it. You know, you can think about, you are taking like 1 or 2 milligram of your sample and you are taking 0.5 ml of solvent. So solute and solvent ratio, which one is higher? Solvent. So if you are not using deuterated solvent and you want to use non-deuterated solvent, that solvent that has the hydrogen. For example, you use, instead of CdCl3, if you would like to use CHCl3, then which peak you will observe? CH, only one CH, because that has the proton and is a huge peak that you will observe, and you will not be able to see your own sample signals because of the comparison. That has a huge amount, definitely it will be recorded first as a proton, right? And your sample, which is 1 milligram or 2 milligram or 3 milligram, 5 milligram, it has no comparison with the solvent. Your solvent is much more as compare your sample. So definitely, if you do not want to use deuterated solvent, or you think it's very expensive, you cannot afford it, so then you have to use some solvent that doesn't have the hydrogen, like CCl4. You should use some kind of solvent, otherwise you will not be able to see signals of your own samples. Got it? All right. So, and based on the solubility, you can also understand the class of the compound. Okay, for example, if you have if your compound is soluble in N-hexane, so definitely it will be hydrocarbons, long chain fatty acids, essential oils, etc. And then in that case, you would definitely like to go for a GCMS analysis and check with the library. Almost everything has been reported. So you do not have to waste time in this. You will not be able to isolate something fancy, fantastic, new from very, very rare chances. And then if your compound is soluble in chloroform or dichloromethane, then it means these could be alkaloid, triterpenes, diterpenes, etc. So these are the classes that are soluble in chloroform or flavonoids. There are many classes. And if your compound is soluble in methanol, so it means since methanol is polar, so definitely there must have several hydroxyl group in the compounds, or must have the sugar, or it might be saponins or the polar alkaloid or peptides. So it's polar compound. If your compound is soluble in water, so it means saponins, glycosides, amino acid, highly polar compound. Highly polar compound. And if your compound is not soluble in any solvent or water, then you have to check if your compound is organic in nature or not. It might be you need to do different type of flame tests, etc. Right? And okay, so determination of elemental composition and molecular mass in formula by using mass spectrometry. So once you have your compound with you, a pure compound, and you would like to proceed, so you need to proceed with mass. So, and it requires very sensitive technique, and it requires very less amount and a very quick technique. And then if you have EIMS done, then if you have the good mass spectrum, then you must have the M positive ion peak. And if you do not have the M positive ion, so then you need to do from some non hard, some soft ionization technique. For example, ESI, CI, FAB, FD, etc. So these you need to go for the soft ionization, but first you need to do hard ionization, EIMS, all right? And then you can proceed for soft ionization. And if you have the good mass spectrum with you, you have the M positive ion with the EIMS, then you need to go for the HREIMS, which is very important. Always remember, you need to always, whenever you write paper or any thesis, you should have the HR and you're calculated, you need to write these values. So it's very important to do the HREIMS, and or if you have the soft technique like ESI done, so HRESIMS need to be done. So high resolution is critically important to be analyzed. Yes. D2O, दोबारा बोले? D2O. Yeah, if your compound have several sugars attached to it, so then it will not be dissolved in methanol, right? Then you have to add, you need to dissolve in D2O, or these are again a small molecule, and these are organic molecules. But with the highly polar compounds, you need to use D2O. Yes.
The convert organic source, we have methods.
Yeah. If you want to, if you have organic salts, then definitely, huh?
Complex organic material. We have methods inside.
Yeah, then here is another, you know, you are putting your sample in a magnet. So you need to have careful if the metal which you are using in your molecules, does it also have the magnetic property or not? So if it does, definitely the spectrum, because the rest of the molecule is organic molecule and it's a complex with any metal. So, but it has a strong impact on the carbons and protons that directly link to this particular metal, and it might be very much upfield shift. It depends, because if you are using, which metal you are using. So if it also has a magnetic property, and you are putting your sample in the big magnet again, so it will has an impact, and and definitely you can record it.
About this, why we should do this characterization, analyzing for the
Yes, yes. You need to know and this is the strategy that you need to follow. You have to do mass first, and then you can proceed for proton. You know, proton is and there are students who are actually submitting their sample, and which is not soluble, completely soluble even and they just randomly write the solvent, and so you know, it's just your waste of time, waste of efforts, waste of money, because if something is not soluble completely, then you cannot get the good result out of it. Maybe partial solubility give you some peaks, but if it, you need to find out the correct solvent first to analyze, because so that you can, your compound should be soluble. We are using solution NMR, we are not using solid state NMR. Okay, so that theory need to be understood to everyone. All right, so and once you have the HREIMS, then you can definitely get the molecular formula, and with the molecular formula, you need to check if this is acceptable or illogical. If illogical, definitely you need to, maybe molecular ion peak is not appeared, so maybe you need to go back and do the soft ionization technique, and you need to check it. And if you get the acceptable molecular formula, logical mass, then you need to search the literature if it is a known compound or unknown compound. If it is a known compound and your mass fragmentation pattern is already known, so then no need to proceed further. You can just report based on the mass, because the fragmentation pattern is very, very clear for each molecule. And for unknown compounds, you can definitely proceed further. And if you would like, and definitely you would like to identify the functional group, we can definitely identify a functional group in NMR, but IR is the best technique for functional group analysis. And it's a non-destructive technique, but it requires 2 micromolar sample, and it can be used in the CHCl3 or as a KBR disk. And so if you get the good IR spectrum, you need to check with the literature and identify the functional group in your molecule. If it is the bad IR spectrum, then you need to check the solubility and the purity of your molecule. And then you need to record the UV spectrum. The UV, again, the non-destructive technique, and it's very sensitive, require only 0.1 micromolar of the sample. And usually methanol as a solvent is being used. And definitely if your compound is not soluble, so maybe you need to reconsider it and check how can you do it, because methanol is the solvent. Otherwise, the other solvents show the peaks and show the absorption actually. And it's a good UV spectrum, then you can. But here you will not get much information except if you have the conjugated double bond. So there should be an absorption and not much information that you can get from UV. But definitely it's one of the requirement. And then you come to the proton NMR analysis. And it's again non-destructive technique, and you need to recheck and be careful about your purity. And there should be no solid particle into it, and degas if possible to remove dissolved oxygen. But in routine NMR, proton NMR case, it is not required, but for NOE, we have to degas the sample. Otherwise, when Dr. Iqbal will discuss with you about the NOE analysis, NOE experiments, then you will understand that during NOE, there is the transfer of magnetization, and this you are going to record. But if there are dissolved oxygen, so magnetization could transfer to the dissolved oxygen. So and that is why we have to degas it, because we do not want a spectrum which doesn't say what is actually happened. So NOE is very important technique, specifically if you want to determine the stereochemistry of your molecule. For any carbon, the stereochemistry you can define using NOE or NOSI technique, and for that we need to degas the sample. And you need to check the solubility at room temperature. Okay, here, as Dr. Iqbal was also mentioning in his lecture, that is extremely advanced and fascinating technique. And you have minus 269 Celsius, and just a millimeter away, you not only at the room temperature, your probe is in room temperature, and not only in the room temperature, you can increase the temperature. You can increase before the boiling point of the solvent. You know, you cannot increase the temperature if the solvent start boiling. So then you cannot record it. So you can increase the temperature. So now you can think and imagine the kind of technology it has. Is minus 269 degrees Celsius, and just centimeter away, you have so much control that not only you can take any room temperature sample analysis, you can run experiments at the higher temperature, you can decrease the temperature as well. So you have so much control. No other technique has give you that much control. So if your compound is soluble in room temperature, that's well and good. If it is not soluble, then you should know at what temperature it is soluble. And then you need, and which solvent you can use in that particular temperature. Definitely deuterated solvents. And that you need to come and increase the temperature. And when you increase or decrease the temperature, you have to wait a lot, because everything affect these are the practical aspect. And you cannot, for example, the room temperature is 298 Kelvin. So in NMR, we discuss everything in kelvins, not centigrade. So 298 is the 25°C. So if you want to decrease the temperature, so if you want to go like 273 Kelvin, you cannot immediately change from 298 to 273. You have to decrease slowly. You have to wait and see the effect. You decrease the temperature 1°Kelvin and then wait. Everything need to be stabilized. As soon as you decrease, there is a shift, and you can monitor and measure it. When we will take you to the NMR lab, then you will see, we will show you how it affects um, the temperature in the recording. We cannot record anything because because that was the not real environment. You have to have that everything is stable, then you record your NMR. Okay, and then 1° and 1° you have to wait. So if you want to for example, decrease the temperature for 5 Kelvin or increase the temperature to 5 Kelvin, it will take half an hour or maybe 20 minutes. Just you need to have a stable temperature when you record your sample. All right, so you have that much control. You can increase, but in cryoprobes, again, there is another technology that we are using. We have two 600 cryoprobe, one 500 cryoprobe, and one 800 cryoprobe. So they are more sophisticated. There's a limit. We cannot increase the temperature very high in cryoprobes. Otherwise, there are specific specialized probes. And it actually, as a matter of fact, because of the cryoprobe, Dr. Iqbal will discuss all these technology with you. And the sensitivity of 800 megahertz is, because of the cryoprobe, is actually about 1 gigahertz magnet because of this one. And the sensitivity of 600 megahertz with cryoprobe is actually around 800 megahertz. So, but the resolution doesn't change. Resolution with the cryoprobe increase the sensitivity, but not the resolution. So, sir will be discussing with you these things later on. Yeah. It depends which sample and what you want to do. It depends. It depends on you, who and what you want to do. For example, if someone wants to see the impact of temperature on hydrogen bonding, okay, just an example for the small molecule, and you have sometime intramolecular hydrogen bonding, you have intermolecular hydrogen bonding, right? The two molecules can hydrogen bond with each other with your 2 milligram or 3 milligram of the sample, or they have some intramolecular hydrogen bonding within the molecule. So if you want to study the hydrogen bonding, you may need to change the temperature. And you may need to check at different temperature and check at a variety of temperature, that what temperature has an effect on the hydrogen bonding. So it depends your need. NMR have more than 1,000 type of experiments. So someone that we are doing here is just the routine, but it depends. You can ask, you can study and ask that I want to do this experiment. That's possible that we can do it. There are more than 1,000 experiments in its library, and you can design your own experiments also. you can write its algorithm by yourself. So, and it's people usually done this also. And mostly in those who are working in biomolecules. They sometimes have to write their own algorithm, yeah, own experiment.
You know what the topic for implication about the compound?
What?
You said we can make our experiment depends on the cinema, not only for identification. We will know what the structure of this compound. For example, if anyone has experiment to study by time, what if he has experiment like kinetic?
Yeah, you can do it. You can design your own experiments. We in our research group, we have been doing this enzyme inhibition. You know, we have the substrate, we have the enzyme, and we design the experiment that we want to see the diminishing of some signal and increment of the product signals. So that depends on the time. You can design your own experiment. You can do a lot of things because these all things possible because it's very slow technique. That is the reason. You have so much control that you can do lots of things with your magnetization vector M naught until it goes back to the z-axis. So whatever the time you have, you have magnetization vector M naught that Dr. Iqbal explained you. When you give a pulse, it comes here on XY plane until, and it's just moving, you know, until it go back. So whatever you do, there is a relaxation phenomena. It's going back to its original state. So until that time, you can manipulate with the magnetization vector. Okay, so you have so much time available to design your experiment, to play with your magnetization vector, your M naught. Okay, and that is only possible in NMR. That's why it's very fascinating. It's very expensive. Like Dr. Iqbal tell you about $2 million, the 800 megahertz that we have, and it's the cheaper one that we got. You know, I was in Germany the same year, 2016, my supervisor there, he got the same instrument with $2.6 million. But Dr. Iqbal, mashallah, is very capable of negotiating with them to bring the price down. And $2 million in Pakistani rupee means, yeah, I think six, I don't know, so much, huh? What? No. Yeah, I think it's 600. I don't know. I need to check. It's difficult because we do not have seen that much money yet. So it's difficult to calculate. 2 million is okay. All right. So okay. So when we have the we need to check the solubility at the room temperature, and it is required 1 micromolar of the sample. And you know, NMR is, proton NMR is the most sensitive one. Most sensitive. We are happy at least proton is the most sensitive nuclei. You can easily get it. All other nuclei is very, you know, for C13 NMR spectrum, this proton NMR spectrum is finished in 2 minutes, 3 minutes time. The similar one-dimensional NMR spectrum I'm talking about, the one-dimensional C13 require overnight at least 36 or 32 or 64,000 scan, and it require only 16 scan. So you can think about so how sensitivity and the natural abundance of C13 is always very important. And here is the, if you get the good NMR spectrum, then you can proceed further. You get the bad NMR spectrum, you need to check the solubility and purity again. And when you have the good NMR spectrum, you can check the integration and compare it with your formula and calculate the J value, check the literature. If it is a known compound, then you need to stop working. And if you have the unknown compound, then you need to go for other techniques like COSY, J-resolve, NOSY, TOXY, HMQC, HSQC, HMVC, lots of experiments. And then you have to identify a structural fragment. For unknown compound, only proton NMR is usually not enough to get the structure. You need to have C13 NMR and you need to have the 2D spectrum also with you. Okay, so now you have the problematic one, the C13, where C13 nuclei is around 6,000 times insensitive as compared to proton. You know, because of its gyromagnetic ratio, which is 1/4 of the proton, and its natural abundance, which is only 1.1%. And on the other hand, we have proton, which is 99.998%. So the natural abundance is a lot. So that is why altogether C13 in natural abundance is 6,000 times insensitive as compared to the proton. If you come and you need to record the broadband spectrum. Broadband is the 1D spectrum of you will Dr. Iqbal will be discussing all these different type of the spectrum and its experimental, how it lead to be the theory behind it. So broadband spectrum is the one-dimensional proton, one-dimensional C13 NMR spectrum. And then you also have depth NMR, which is depth is distortion-less enhancement by polarization transfer. So little bit acronyms you need to perhaps remember. So and then there are depth 135 usually, or depth 90 we usually record to identify again methine, methyl, and methylene carbons. And then you have, and that requires, since it is again non-destructive technique, but it's very insensitive, so require more amount. Okay, and when you have the good spectrum, you need to check. And there is one important beauty about the C13 NMR as compared to the proton. And if you have seen the proton NMR, the scale is very small. You know, from 0 to 14 or sometimes 12, you know, less than that. So that is the overall scale. While in C13 NMR, you have a scale from 0 to 220. Okay, so in proton NMR, though all informations are there, but they are overlapped often. Even if it's a very medium-sized molecule, the peaks are overlapped. And due to these overlap, you need to, you know, this proton NMR spectrum have all the information you required it, but you need to decipher it. So that is why 2D is required. So while the C13 NMR spectrum has a bigger scale, like 0 to 220. So there are very, very, very less chance for overlapping of the signal. Okay. And here, in proton NMR spectrum, the advantage is you can integrate it. You know, you can, you know, sometimes NMR persons who are doing something for you, they are technicians. So that's why purity is very important. You know, if you do not have the pure compounds, so you may integrate an impurity as one hydrogen, and the rest will be integrated accordingly. So you need you know your compound, you know which one should be the one proton. So then you need to identify, and then rest will be integrated as per your expertise. Okay, so that you have to do carefully, because otherwise the number of proton will be different than whatever you are getting from mass. Okay, so that is, yes.
The spectra of proton which is the way we see the duality.
Oh, I did not come to yet. I am just talking about the good one.
I will use the same symbol sometimes for the HNMR. How I can start parabolic?
The same sample, if you have the less amount given, then you cannot get the good C13 spectrum. 6,000 times insensitive. Always remember. If you give like 1 milligram sample to proton, you get the beautiful proton NMR spectrum. 1 milligram sample for the C13, you will get maybe few peaks. That's it. Bad spectrum. Okay. So not only the solubility, you need to check the quantity as well. So these are the practical aspects that we need to consider. Okay. And and depth. So we have using depth. Okay. I was telling you, in proton NMR, we can integrate. We know the number of hydrogen. In C13 NMR, we cannot integrate. This NMR is not for the purpose. And again, the reason behind it, because there was in earlier days, there was other techniques in which it's difficult for me to explain right now because we haven't shown you the spectrum. So some of you may understand the J values, right? So who have seen the proton NMR spectrum. So the J value is because of the coupling of one proton with its neighboring proton, right? In C13 NMR spectrum, in earlier days, there was NMR spectrum in which the J values, there was a doublet, there was a triplet. If this carbon is attached to 2 carbons, so this will appear as a triplet. And if one carbon is attached to other carbon, only one, n+1 rule. So doublet and triplet, but the J value is very, very high. It's like this. You have, for example, you have one peak here, and then after few ppm, there is another peak, and in between there is a peak of someone else, other carbon, and then is a peak of another. So much crowded. It's very difficult for someone to identify the coupling partners. The doublet and triplet, the peaks are they have the big J values. They have, in proton NMR, we have J value like sometime in 1 hertz. Maximum we go for 18 or 19 hertz. In carbon, we have J value in hundreds, 150 hertz, 180 hertz, like these kind of 120 hertz. So you can think about the one doublet has a one peak here and the other peak here. And then after some time, then there is another carbon that has another one peak here and the other. So if I will look at this spectra, I will confuse. So these two peaks are the partner, or these two peaks are the partner. How we will identify, and it's important to identify because we want to identify CH, CH2, and CH3. And the reason, because every C13 NMR is attached with a proton which is NMR active. Okay, so it will split because of the proton. If it has a one proton attached to it, it's split into doublet. So methyl, methine, and quaternary carbons we cannot identify. Now we are using depth, and we see only one signal. So, and the other technique that we were using were APT. So that has different peaks. So now we are not, now our life is much easier. You know, we know in depth spectrum, these are CH, these are CH2, and the remaining are the quaternary carbon. So we compare, and we will discuss this when we will be discussing the interpretation. So life is much easier now. Okay, so when you have the good carbon NMR spectrum, you check the signals are well resolved because the spectrum is quite big. The width of the spectrum, and usually is very, very rare chance that there is an overlapping. I have not seen myself like this. And he counted the number of signal corresponding to the number of carbon. So then compare with the HREI EMS, and you have depth 90 and depth 135 that are usually recorded. And depth 90, you can identify only CHs, while depth 135, CH2 are kind of hanging downward, and CH and CH3 are hanging upward. And a quaternary we cannot see because it's the polarization transfer. Distortionless enhancement by polarization transfer. So polarization can transfer only from the high polarization to the lower polarized. So proton to carbon. And quaternary carbon doesn't have the proton attached to it. So the polarization cannot transfer. That's why we cannot observe in the depth NMR spectrum. But it's okay. We have the broadband with us, and that has all the C, CH, CH2, and CH3. So we can just, whatever not present in these two depth are quaternary, and that are present in broadband. Okay. So if you have the bad NMR spectrum, you need to recheck the solubility. You need to maybe give more amount to get the better spectrum. And then you after if you have if you find this compound might be new, then you need to record the 2D techniques such as HMQC, HMBC, HSQC, and so these are inverse NMR technique. In inverse NMR are the techniques in which we see carbon in the mirror of proton. So these are inverse. So it's not directly, we are not directly recording proton like proton NMR spectrum. We are not recording carbon like carbon C13 NMR spectrum. We are recording proton, but proton has the information of carbon. So we are seeing carbon in the mirror of proton. Okay, so most easier word, but we will be discussing about the practical aspect, and the theory Dr. Iqbal will explain as the inverse NMR. These are inverse, most widely used inverse NMR techniques, and inadequate. It's the most fascinating technique, but extremely insensitive. You can think about two C13 in natural abundance together. Only 1.1%. So there definitely there will be some molecule that in which two C13 are together, but it requires the amount is again a problem. You have the limitation of 0.5 ml. How much you can dissolve in 0.5 ml? You cannot have 1 gram dissolve in 0.5 ml of the solvent. The solubility also has a limit. The solvent is 0.5 ml that we have to use. So how much compound you can dissolve into it? Maybe 20, maybe 30 milligram. right? But not more than that. Even 50 milligrams just start precipitating. 50 milligrams is a lot. With the higher solubility, you can maybe up to 25 or 20, 30 milligrams. But solid, if even you have 1 gram of the compound, you cannot dissolve in 0.5 ml, so you have the limitation. And it's very good technique. You can identify the whole carbon skeleton, but because of C13, it's very insensitive technique. They are very, very 1.1% natural abundance. So very insensitive technique. It's a known compound and you don't have to record the 2D spectrum for sure. Okay, so there are various NMR spectroscopic experiments that there are a few. And I told you, when we'll take you to the NMR lab, we'll show you there are thousands, at least 1,000 NMR experiments in its library. But you need to identify that you want to do this experiment and this experiment. That's your work to do. Okay, and then you can ask NMR technical staff that you need to run these experiments. So they have the expertise, we have the expertise. If they cannot do it, so we can optimize. Me, Dr. Sumaira and Dr. Mara, we have been trained in setting up NMR experiments. So we can set up the NMR experiments, but the requests need to be generated from you guys. Okay, so what are the NMR? In one dimension NMR spectroscopy, proton NMR, C13 NMR, and in proton, we have NOE, and then 1D and 2D NMRs. And then C13, we have broadband of resonance. So these all you will be discussing. The theory will be discussing spin echo experiment, polarization, transfer experiments. So nowadays, almost every experiment has the polarization transfer. And Dr. Iqbal will teach you the concept of polarization transfer, because to increase the sensitivity of carbon. And it's like borrowing money. I think Dr. Iqbal has given this example. If someone is poor, we can borrow the money from someone and just to show the back balance, sometime to get visa and then return back. So this is the polarization transfer. So just getting polarization transfer to increase the sensitivity. And there are two and multi-dimensional NMR, homonuclear and heteronuclear. Homonuclear, you observe like proton, proton, or carbon, carbon, and heteronuclear, proton, carbon, proton, nitrogen, they are different. So homonuclear, you have the J resolve, they have POSI, toxis, inadequate, and doses, and rosy, nosy, dosy. Okay, and then heteronuclear, you have inverse NMR like HSQC, HMBC, HMQC, and you have colloq, headcore, and these are old time, means like no one is using nowadays, but the experiments are there, so you can definitely record it. And because these inverse NMR are far more sensitive as compared to these colloq and a headcore. And what? Yeah. Not only these, I told you there are thousands experiments. These are all experiments. So each individual technique is experiment. So there are thousands experiments in the libraries there. So, but you need to identify which technique you need, because interpretation is your job. Okay, we are trained to set up any experiments that is required, and but demand from your side. Okay, so any questions so far further? Any question from online participant? Yeah.
Concentration, how the concentration can affect. But what I should see if I use for example the simple compound like ethanol, I should say for use ethanol. The big difference in what?
if you have at least the minimum concentration required to different type of the experiments. If you have a small like you said, ethanol, so there are only 2 carbons there. Very small quantity is fine. Analysis depends, again, how big your molecule is. For in an average, you need to have at least 3 to 4 milligrams available for all good proton C13 and spectrum, because we have the very good now all these instruments are most upgraded one.
There is one question, what the effect of the sensitivity?
Concentration has some effect, definitely, but there is a limit. You can increase the sensitivity based on the concentration, but the solubility again is a 0.5 ml, that small quantity. Okay, so you can have like 10 milligram of the sample, then maybe 4 scans are required. Instead of 128 scans, you can get the spectrum in 4 scans. Okay, scan is each experiment, so it's just overlap with each other. We'll discuss it further. Yes.
Equation, the probe. Now, before the cryo probe, first question.
What? Before
the cryo probe, which is the most advanced?
We have all the room temperature probe as well. We have only 4 cryoprobes. We have 13 NMR spectrometer, and we have 4 cryoprobes. The remaining are room temperature probes. Okay, and with the cryoprobe, there is a room temperature probe also, but we definitely, when we have a cryoprobe, why we need to install the room temperature probe.
Now the question, can you upgrade the room temperature probe to the cryoprobe?
Yes, yes. You can always upgrade.
And is this
These are 2 different probes. Okay, cryoprobe is different and room temperature probe is different. For each cryoprobe equipment, there is a room temperature probe as well available. But once we have the cryoprobe system, why we need to remove the system and have the room temperature probe? It's more sensitive, definitely. Okay. And there is a question online, is compound having mass less than 100 Dalton good for biological activity? Biological activity, you can definitely check for any molecular weight. There is no limitation for the molecular mass. Are these slides going to be shared? Yes, these slides will be shared. Yeah. MCQs 5 Kevin. Okay, the question is, what is the C13 resonance frequency on 600 megahertz NMR spectrometer? So, what is the difference between the gyromagnetic ratio between the proton and C13? 1/4. Okay, so gyromagnetic ratio of carbon C13 is 4 times less as compared to the proton. So whatever, that's very interesting question that Navera has asked. So in all the NMR equipments, megahertz were written. Megahertz are the frequency of the proton. So this is the proton 800 megahertz mean the proton frequency will be 800 megahertz, but we are now used to it using this. We are not writing Tesla on this equipment. Dr. Iqbal told you that 800 megahertz, 18.8 Tesla, but we are not writing to it. We are using proton as a standard and we are just used to it. So Now, the question is, when there is 800 megahertz or 600 megahertz or 400, whatever, uh, equipment, so what would be the frequency of carbon? So these are the frequency of proton. So what would be the frequency of carbon? Divide by 4. Okay, so 600 divided by 4 means 150 megahertz. So C13 frequency will be 150 megahertz on 600 megahertz NMR equipment. And for 800 megahertz, divide by 4, 200 megahertz. So C13 NMR frequency or 800 megahertz will be 200. So when you write your manuscript or paper or your thesis for carbon, you cannot write 600 megahertz. You have to write 150 megahertz. Okay, good.
Could you please explain question 7?
Okay. So another question, could we use more than 0.5 ml solvent, and what is the ratio we could take our sample and solute? Okay, all right. So, you know, there is, okay, I will take this. Just think about, suppose this one is an NMR tube. Okay. And you know your sample will face the radio frequency. Okay, the radio frequency should hit the sample. And when you place your sample inside the probe, so you know this much, this is the face of your NMR tube that is actually exposed for the radio frequency. Okay, so that much simple one. So thus your solvent below this one and your solvent above this one. Even you fill up the tube has no effect. So 0.5 ml is just right there, little bit up, because you know whenever the solvent's there is a curve, you know, small curve. Yeah, so we do not want this to interfere. So we cannot have less than 0.5 ml. So otherwise it will come to face the radio frequency. So our peaks will be disturbed. Okay, I think it's clear.
Question number 7.
I'm looking forward to NMR that will analyze compound and also provide structure. Yes, sure, inshallah.
Question number
No,
7.
first, you asked something? Question 7. Okay, so here there was a typo that Dr. Sumaira explained. The spin quantum number of N14, not N15, is 1. Okay, so the formula is 2i plus 1. So I is 1. So 2i plus 1 means 3. So what would be the states? -1, 0, plus 1. Okay. And what you asked? Okay. So N14 means has a spin quantum number 1. And the formula in the presentation of Dr. Iqbal, he showed 2i plus 1. So I is 1. So 2 multiplied by 1 plus 1 means 2 plus 1 means 3. So 3 states means -1, 0, plus 1. Okay? Yes.
Calculation constant sensitivity of carbon. I use measured over and notice that it gets 151 instead of from 600 megahertz. I don't know why.
I don't know. I have never used Nova. I always use top spin, but whatever written on your spectrum, this is the frequency that your nuclei is facing. And whatever read by Nova, this is another third-party software, so I don't know. So whatever written in the Bruker, so I myself always use top spin for analysis and everything. And I never used this Mastronova, but it's whatever you see in the spectrum is the one that your nuclei faced in the top spin is from Bruker. This is the same software which is we use to run the experiment. Yes.
Sorry. I remember before 1 year, conference, so I think maybe we should ask for mixture. I asked him how we can do it for 10 days.
You can definitely record whatever you want to record on because whatever soluble and put it in NMR tube and you can record it. Definitely no problem. Problem is analysis. Okay. Recording is no problem. Whatever, how, even the whole plant mixer is thousands of compound, you can record it. How you would analyze?
Something.
Yeah, maybe. Okay, thank you. Oh, one more question. Can we design experiments in NMR employing artificial intelligence? Yes. If yes, would it be helpful in increasing the resolution somehow? Not artificial intelligence, there is a mathematical transformation that are, whatever that's, you can manipulate the, using the mathematical calculation, because whatever signals that you get is definitely transformed into the signal, this time domain signal into the frequency domain signal. And there are lots of parameters in the top spin available that you can manipulate and increase the sensitivity, or not, like you can get better spectrum, but you have to play around with this mathematical calculation. I don't know about the artificial intelligence use in that case. Thank you. Thank you. Thank you, everyone, online participants, and Khulafis.